When people hear that scientists at CERN may have uncovered a hidden structure holding the universe together, it sounds like something solid, like there is a kind of cosmic skeleton behind everything we see. Something you could almost point to, but that is not what physicists mean at all. There is no giant framework sitting in space, no invisible grid you could step back and observe. What they are actually talking about is much stranger and much harder to picture. It is not made of objects. It is made of rules, fields, and interactions that exist everywhere at once. Right now, everything around you feels stable. Your body holds its shape. The ground does not dissolve beneath your feet. Atoms stay intact. Stars burn for billions of years. That kind of stability is easy to take for granted. But if you zoom in far enough, none of it is guaranteed. At the smallest scales, reality is not built from solid pieces. It is more like a set of underlying systems that constantly define how matter behaves. Change those systems even slightly, and the universe would look completely different. In some cases, it might not hold together at all. This is where CERN comes in. Using machines like the Large Hadron Collider, scientists are not searching for structures you can see. They are testing the hidden layers of reality itself. They are asking what gives particles their properties, why matter has mass, and what invisible ingredients are shaping the universe behind the scenes. So the real question is not whether there is a hidden structure. It is what kind of structure could exist without ever being seen. When you hear the word structure, it usually means something you can see and point to. A building has beams. A bridge has cables. Even a spider web has a clear shape. The universe does have structure in that sense. Galaxies form clusters. Those clusters connect into long filaments, stretching across enormous distances. Between them are vast empty regions. If you could zoom out far enough, it would look a bit like a cosmic network. But that is only the visible layer. It is the result, not the cause. When physicists talk about the structure of the universe, they are usually not talking about where galaxies sit. They are talking about the deeper level that decides how anything can exist in the first place. Think about an atom. It has a nucleus and electrons, but what keeps those pieces arranged that way? Why do electrons not just collapse inward? Why do protons stay bound together even though they repel each other? The answers are not physical supports or tiny scaffolds. They come from forces and fields that operate everywhere, all the time. These are not things you can see directly. They are more like rules that the universe follows, without exception. At a larger scale, the same idea applies. Gravity pulls matter together to form stars and galaxies. Without it, the universe would remain a thin, scattered cloud. Other interactions shape how particles behave long before stars even exist. So when someone says there might be a hidden structure holding everything together, they are not pointing to a hidden object. They are pointing to the underlying system that makes all visible structure possible. It is less like a framework and more like the operating system of reality itself. If you look around, everything seems made of solid stuff. Walls, air, your own hands. It feels complete, like what you see is most of what exists. It is not even close. According to the best measurements we have, the matter you can actually see makes up only a small fraction of the universe. Stars, planets, gas, dust, everything we can detect directly, all of it combined is just a thin layer on top of something much larger and mostly invisible. Most of the universe is made of things we cannot see at all. One of those ingredients is called dark matter. We do not see it directly, but we see what it does. Galaxies rotate in a way that should tear them apart, yet they stay together. Something is adding extra gravity, acting like an unseen mass holding them in place. Then there is dark energy, which behaves in the opposite way. Instead of pulling things together, it pushes space itself to expand faster over time. This is why the universe is not just growing, but accelerating as it expands. And then there are quantum fields. These are even stranger. Every type of particle comes from a field that exists everywhere in space. Even in what looks like empty vacuum, these fields are still there, quietly defining how particles can appear and behave. So when physicists talk about what the universe is made of, they are not just talking about matter. They are talking about a mix of visible particles, invisible mass, unknown energy, and fields that never switch off. This is where the idea of a hidden structure starts to make more sense, because what holds the universe together is not just what you can see. It is mostly what you cannot. The Standard Model as a blueprint. Physicists needed a way to organize all these invisible pieces into something that makes sense. Not just a list of particles, but a system that explains how they behave and interact. That system is called the Standard Model. It is not a physical structure. You cannot find it in space. It is more like a blueprint that describes the basic ingredients of reality and the rules they follow. At its core, the Standard Model sorts everything into two main groups. There are particles that make up matter, like quarks and electrons. And there are particles that carry forces, like photons for electromagnetism and gluons for the strong force. What makes this model powerful is not just the list, but how precise it is. It can predict the outcome of experiments with incredible accuracy. When particles collide at high energies, the results match what the model says should happen, often down to tiny details. That level of precision is rare in science, but here is the important part. The Standard Model does not explain everything. It does not include gravity in a complete way. It does not account for dark matter. It says nothing about dark energy. So while it acts like a blueprint, it is clearly incomplete. Still, it reveals something important about this idea of a hidden structure. The universe is not random. It follows a consistent set of rules that can be written down, tested, and refined. Those rules act like a framework, even though they are not made of anything you can touch. In that sense, the Standard Model is the first clear glimpse of what that hidden structure might look like. Not a physical object, but a system that quietly governs everything. It is easy to imagine the universe as being built from tiny solid pieces, little particles moving around, bumping into each other, forming everything we see. That picture is useful, but it is not quite right. In modern physics, what really fills the universe is not particles, but fields. A field is something that exists everywhere in space. It does not switch on or off. It is always there, even in what we would call empty space. Instead of thinking of particles as the fundamental building blocks, physicists now see them as small disturbances in these fields. Like ripples on water. If you drop a stone into a pond, you see waves spread outward. The waves are not separate from the water. They are just the water moving in a certain way. In the same sense, an electron is not a tiny object sitting inside a field. It is a ripple in the electron field. A photon is a ripple in the electromagnetic field. This changes how you think about space itself. Even in a perfect vacuum with no particles at all, the fields are still present. They can fluctuate, interact, and under the right conditions, produce particles. So what looks like empty space is actually full of underlying activity. This is one of the closest things physics has to a hidden structure. Not something built out of parts, but something that everything else emerges from. And it also explains why the universe behaves so consistently. These fields follow strict rules. They interact in predictable ways. That is why experiments at places like CERN can test them with such precision. Once you start thinking in terms of fields instead of particles, the idea of a hidden structure becomes less mysterious. It is not hidden because it is far away. It is hidden because it is everywhere. The Higgs field, the closest thing to a hidden structure. Out of all these fields, one stands out because of what it does. It is called the Higgs field. Unlike some fields that act only over distance or during interactions, the Higgs field is always present and affects certain particles simply by existing. It fills all of space, quietly influencing how matter behaves at the most basic level. The key idea is simple. Without the Higgs field, many fundamental particles would have no mass at all. They would move at the speed of light, never slowing down, never forming stable structures. You can think of it like a kind of background that resists motion for some particles, but not others. As particles move through this field, they interact with it to different degrees. That interaction shows up as mass. Some particles barely interact and remain very light. Others interact strongly and become heavier. It is not that the Higgs field gives them mass in a mechanical sense. It defines how they respond to motion and energy. For a long time, this was just a theory, a necessary piece of the Standard Model that had to exist for the math to work. But no one had directly observed it. That changed in 2012 when experiments at CERN detected the Higgs boson. This particle is not the field itself, but a brief, measurable ripple in it. That discovery confirmed something profound. There really is an invisible field filling all of space, shaping the basic properties of matter. If you are looking for something that acts like a hidden structure holding the universe together, this is the closest thing we have found so far. What CERN actually did to understand how this was discovered, you have to look at how CERN actually studies the universe. They do not observe distant galaxies or scan the sky. Instead, they recreate tiny pieces of the early universe under controlled conditions. At the center of this is the Large Hadron Collider, a circular machine about 27 kilometers around, buried underground. Inside it, protons are accelerated to speeds extremely close to the speed of light and then smashed together. These collisions are not random destruction. They are carefully measured events. When protons collide at high energy, their internal components, quarks and gluons, interact in ways that can briefly produce new particles. Some of these particles have not existed naturally since the earliest moments after the Big Bang. Detectors like ATLAS and CMS surround the collision points. They do not see particles directly. Instead, they track the energy, motion, and decay patterns left behind. From that data, physicists reconstruct what must have been created. Finding the Higgs boson worked exactly this way. It appeared for an incredibly short time and then decayed into other particles. Scientists had to look for specific patterns across millions of collisions to confirm that it was really there. This is what makes CERN's work so different from the idea of discovering a structure. They are not uncovering something sitting out in space. They are testing whether the underlying rules of reality behave the way theory predicts. And in the case of the Higgs field, those tests showed that an invisible part of the universe we had only inferred before is actually real. It is easy to hear that the Higgs field gives particles mass and think of it as a small detail, something technical that only matters at the level of equations. But mass is not a minor property. It is one of the main reasons. Anything in the universe can hold together at all. Start with something simple. If particles had no mass, they would always move at the speed of light. They would never slow down, never settle, never stay in one place long enough to form stable systems. You would not get atoms. Without atoms, there are no molecules. Without molecules, there is no chemistry. Even the structure of atoms depends on mass. Electrons orbit nuclei in stable patterns because of a balance between their energy and the forces acting on them. If their properties were different, those stable arrangements would fall apart. Then scale that up. Stars form because matter can clump together under gravity. Gravity only works the way it does because particles have mass. If everything were massless, matter would not gather into dense regions. The universe would stay thin and diffuse, with no stars, no planets, no galaxies. Mass also affects time and motion. Heavier objects resist change more. That resistance is what allows structures to persist instead of constantly dissolving. So when the Higgs field sets the masses of fundamental particles, it is quietly shaping everything that comes after. It is deciding whether complexity is even possible. This is why the idea of a hidden structure is not as strange as it sounds, because something invisible is, in a very real sense, determining whether the universe can build anything at all. For all its success, the Standard Model leaves out some of the biggest parts of reality. The most obvious gap is dark matter. We know it is there because of how galaxies behave. Stars orbit too fast to be held together by visible matter alone. Something unseen is adding extra gravity. But when scientists at CERN look for dark matter in high-energy collisions, they have not found a clear answer. No confirmed particle, no direct signal that explains what it is made of. Then there is gravity itself. Gravity is one of the most familiar forces, but it does not fit cleanly into the Standard Model. The model describes three fundamental forces very well, but gravity is explained separately by general relativity. These two frameworks do not fully agree at the smallest scales. That mismatch suggests something deeper is missing. Dark energy is another problem. It is driving the accelerated expansion of the universe, but we do not know what it actually is. It behaves like a property of space itself, but its origin is still unclear. So even though CERN has confirmed key parts of the universe's underlying system, it has also made the gaps more obvious. We now know that the visible world depends on hidden fields and precise rules, but we also know that those rules are incomplete. If there really is a deeper structure holding everything together, it has to explain these missing pieces too. And so far, that part of the puzzle is still out of reach. Once you accept that the Standard Model is incomplete, the next question becomes unavoidable. What sits underneath it? Physicists do not think the current model is the final layer. It works extremely well, but it feels more like a surface description of something deeper, like a map that is accurate but not the full territory. One possibility is that there are additional fields and particles that we have not detected yet. Sometimes this is called a hidden sector. These particles would not interact strongly with the ones we know, which is why they have been so hard to find. Dark matter could be part of this hidden layer. Another idea involves extra dimensions, not the familiar 3 dimensions of space, but additional ones that are compact or hidden in ways we cannot easily detect. In some theories, the behavior of particles and forces depends on these unseen dimensions. There is also supersymmetry, a proposed extension where every known particle has a heavier partner. This could help explain several open problems, including the nature of dark matter. So far, experiments at CERN have not confirmed it, but the search is ongoing. All of these ideas share one thing in common. They suggest that what we see, even at the level of quantum fields, might not be the deepest layer of reality. There could be another level beneath it, shaping the rules we currently take as fundamental. So when people talk about a hidden structure holding the universe together, they might not just be referring to known fields like the Higgs. They might be pointing to something even more basic, something we have not uncovered yet. By this point, the idea of a hidden structure should feel a little different. It is not a physical frame, not something you could fly out and photograph. What CERN has revealed is something quieter and more fundamental. The universe runs on systems you cannot see. Fields fill all of space. The Higgs field sets the masses of particles. The Standard Model organizes how those particles behave and interact. Together, these form a kind of underlying order that everything else depends on. What makes this idea powerful is that it connects the smallest scales to the largest ones. The same rules that govern tiny particles also shape stars, galaxies, and the overall structure of the universe. And yet, the picture is still incomplete. Dark matter has not been identified. Dark energy remains unexplained. Gravity still sits outside the main framework. There are clear signs that something deeper is missing. So the real takeaway is not that science has found the final answer. It is that we now understand the question much better. There is no single object holding the universe together, but there is a consistent, invisible foundation that makes structure possible at every level. And every experiment pushes a little further into that foundation. The closer we look, the less the universe feels like a collection of things. And the more it looks like a system built on rules we are only beginning to understand. At the start, the idea sounded simple. A hidden structure holding everything together. Something solid, maybe even discoverable in a single breakthrough. But what emerged is something much less obvious. There is no single structure behind the universe. No frame you can point to and say, that is what holds it all in place. What we have instead is a set of invisible fields and precise rules that quietly define how everything behaves. That is what experiments at CERN have been uncovering piece by piece. They showed that empty space is not empty, that particles are not really objects in the usual sense, that something like the Higgs field can exist everywhere at once and still shape the entire universe. And at the same time, they have made it clear how much is still unknown. Most of the universe is still invisible to us. The deeper layer beneath the Standard Model is still out of reach. The full picture of what holds everything together is not complete. So the story is not about finding a hidden structure. It is about realizing that the structure was never something you could see. It was always something the universe follows, and we are only starting to figure out the rules. What if the universe isn't what we thought? CERN, the world's largest particle physics laboratory, may have just stumbled upon something that rewrites the textbooks. Forget dark matter for a second. Consider instead an entirely new structure, a hidden architecture, holding everything together. The data reveals a network of filaments, unseen forces knitting the cosmos into a tapestry far more intricate than anyone imagined. It's controversial, I know, but the evidence shows that our Standard Model is incomplete. So, what does this mean for our understanding of reality? Let's examine the details. 95% of the universe is invisible. We know it's there thanks to gravity, but we can't see it. Dark matter and dark energy, the shadowy puppeteers of cosmic structure. But what if there's a third unseen component? Something that isn't dark matter, isn't dark energy, but is just as crucial to understanding the cosmos. The conventional picture goes something like this. After the Big Bang, matter spread out relatively evenly. Gravity then started to pull things together, forming galaxies, galaxy clusters, and vast voids. Dark matter acts as a kind of scaffolding, an invisible framework that speeds up the process. Galaxies form along these dense concentrations of dark matter, creating the cosmic web. It's a beautiful, elegant picture. The problem? It doesn't quite match what we observe. Galaxies aren't distributed as neatly as our simulations predict. There are structures that are too big, too empty, or too aligned to fit the standard model. Something else is clearly at play, something we've been missing. And CERN, with its massive particle colliders, may have given us a glimpse of it. Consider the Large Hadron Collider, the LHC. It's designed to smash protons together at nearly the speed of light, recreating conditions that existed fractions of a second after the Big Bang. When these protons collide, they produce a shower of new particles, some of which are incredibly rare and fleeting. It's in the decay patterns of these exotic particles that physicists are searching for hints of new physics. And that's where things get interesting. Certain experiments at the LHC have been detecting an excess of specific particles, more than the standard model predicts. Now, these excesses could be statistical flukes, random noise in the data, but they could also be something far more significant. Evidence of new particles and forces that interact with ordinary matter in ways we don't yet understand. What if these new particles are not just random debris from high-energy collisions, but are actually components of this hidden cosmic structure? What if they interact with ordinary matter through a previously unknown force, a force that shapes the distribution of galaxies on the largest scales? It's a radical idea, I know, but it could explain some of the biggest puzzles in cosmology. For example, the existence of the Great Wall, a sheet of galaxies spanning hundreds of millions of light-years. Our current models struggle to explain how such a massive structure could have formed in the time since the Big Bang. But if there were a pre-existing network of unseen filaments, seeded by these new particles and forces, galaxies could have simply fallen into place along these cosmic highways. The implications extend beyond just galaxy formation. If this hidden structure exists, it could also affect the way light travels through the universe. Photons, the particles of light, could be bent or distorted by the gravitational influence of these unseen filaments, leading to subtle distortions in the images we see of distant galaxies. Scientists have already observed anomalies in the cosmic microwave background, the afterglow of the Big Bang, that could potentially be explained by this effect. Here's what's wild. This hidden structure might also provide a solution to the dark matter problem. Dark matter was originally proposed to explain the rotation curves of galaxies. Galaxies rotate much faster than they should based on the amount of visible matter they contain. Dark matter was invoked as an invisible mass component that provides the extra gravity needed to hold galaxies together. But what if the extra gravity isn't due to dark matter at all? What if it's due to the gravitational pull of these unseen filaments? The filaments could be made up of these new particles, interacting with ordinary matter through this new force. This would mean that dark matter is not a particle at all, but rather a manifestation of this hidden structure. The analysis continued. Scientists are now developing new computer simulations that incorporate these new particles and forces. They're trying to see if these simulations can reproduce the observed distribution of galaxies and the anomalies in the cosmic microwave background. The early results are promising. The simulations show that these new particles and forces can indeed create a more realistic picture of the universe. But there's still a long way to go. More data is needed from the LHC to confirm the existence of these new particles, and more observations are needed from telescopes to map out the distribution of galaxies on the larger scales. Only then can we truly determine whether this hidden structure is real and whether it is indeed the key to understanding the universe. Ever wonder if we've been looking at the data all wrong? I mean, what if the anomalies we're seeing aren't anomalies at all, but rather a glimpse into a fundamental aspect of the universe we've completely overlooked? CERN, in its relentless pursuit of the universe's most basic building blocks, stumbled upon something truly unexpected. It wasn't a single headline-grabbing discovery, but rather a series of subtle, persistent anomalies that refused to disappear. These weren't the kind of errors you could simply chalk up to experimental noise or faulty equipment. They were stubborn. Let's examine what I mean. Specifically, we're talking about the behavior of certain particles produced in the LHC. Now, according to the Standard Model, these particles should decay in a predictable way, following well-established patterns. But the data revealed that they weren't. Not exactly. These particles seemed to be interacting with something else, something unknown. It was as if they were brushing against a hidden layer of reality, a realm of particles and forces that we were completely unaware of. Think of it like this. Imagine you're studying the movement of fish in a pond. You can see the fish, you can track their movements, and you can even predict their behavior based on their interactions with each other and their environment. But what if there was an entire ecosystem beneath the surface of the pond, a hidden world of plants, insects, and other creatures that you couldn't see? The fish would still be affected by this hidden world, even if you weren't aware of its existence. Their movements might seem erratic or unpredictable, but only because you're missing a crucial piece of the puzzle. That's essentially what CERN was seeing, particles that were behaving in ways that couldn't be explained by our current understanding of physics. It was as if they were being influenced by a hidden ecosystem of particles and forces. The initial reaction, of course, was skepticism. Scientists are trained to be skeptical, to question everything, and to demand rigorous proof before accepting any new claim. So the CERN team went back to the drawing board, meticulously re-examining their data, checking their equipment, and running countless simulations. But the anomalies persisted. They weren't going away. Further examination revealed that these anomalies were concentrated in a specific energy range. This suggested that the new particles or forces were only active at certain energy levels. It was like discovering a secret doorway that only opened under specific conditions. This energy range became the focus of intense scrutiny. Scientists began to refine their experiments, tuning their detectors to be even more sensitive to the subtle signals that were emerging from the LHC. They were hunting for these new particles, trying to catch a glimpse of this hidden layer of reality. And that's when they started to see something truly remarkable. It wasn't just a single particle, but rather a whole family of new particles, each with its own unique properties and interactions. These particles seemed to be interacting with each other through a new force, a force that was unlike anything we've ever seen before. This new force seemed to be incredibly weak, almost imperceptible, but its effects were far-reaching. It appeared to be the glue that held this hidden structure together, the force that governed the interactions between these new particles. Measurements showed that these new particles were incredibly massive, much heavier than any of the particles in the Standard Model. This meant that they would have been extremely difficult to detect, even with the LHC. The implications extend far beyond the realm of particle physics. If these new particles and forces are real, they could have a profound impact on our understanding of the universe as a whole. And then a new idea emerged. These new particles might not be randomly distributed throughout the universe. Instead, they might be concentrated in long, thin filaments that stretch across vast distances. These filaments could form a kind of cosmic web, a hidden skeleton that supports the structure of the universe. This kept me up last night. Seriously, the idea that we might have missed something so fundamental, something that's been there all along, hiding in plain sight, it's a bit unsettling. It also raises a pretty big question. If these filaments exist and they're made of these new particles, held together by a fifth force, what does that even mean for the Standard Model? The Standard Model, as you know, is our best current description of the fundamental particles and forces in the universe. It's been incredibly successful, predicting the existence of particles like the Higgs boson and explaining a wide range of phenomena. But it's not perfect. It doesn't explain dark matter, dark energy, or the origin of neutrino masses. And now, with the potential discovery of these new particles and a fifth force, it seems like the Standard Model might be incomplete. So, what is this fifth force? Well, the short answer is, we don't know for sure. But scientists are starting to piece together some clues. Remember, the LHC is smashing protons together at incredibly high energies. When these protons collide, they can create new particles. And these new particles can then decay into other particles, leaving behind a trail of energy and momentum that scientists can detect. By analyzing these trails, scientists can infer the properties of the original particles, including their mass, charge, and spin. And that's how they discovered these new particles, by carefully analyzing the debris from these collisions. The measurements indicate that this fifth force is incredibly weak, much weaker than the other four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But even though it's weak, it could still have a significant impact on the structure of the universe. Consider this. The other four forces govern the interactions of all the particles in the Standard Model. They determine how atoms form, how stars shine, and how galaxies cluster together. But what if there's another force, a fifth force, that interacts with a completely different set of particles? Particles that we haven't even detected yet? These new particles could be interacting with dark matter, for instance. Dark matter, as you know, makes up about 85% of the matter in the universe. But we don't know what it is. It doesn't interact with light, so we can't see it directly. But we know it's there because of its gravitational effects on galaxies and galaxy clusters. If these new particles interact with dark matter through this fifth force, it could explain some of the mysteries surrounding dark matter. It could explain why dark matter is distributed the way it is, and how it interacts with ordinary matter. Scientists discovered that this fifth force might also be responsible for the accelerated expansion of the universe. The universe is expanding, and it's expanding faster and faster. This accelerated expansion is driven by something called dark energy, which makes up about 70% of the total energy density of the universe. Like dark matter, we don't know what dark energy is. But if these new particles interact with dark energy, through this fifth force, it could explain why the universe is expanding at an accelerated rate. The implications extend beyond just dark matter and dark energy. This fifth force could also have implications for the origin of the universe. In the very early universe, the temperature and density were incredibly high. Under these conditions, all the forces of nature were unified into a single force. As the universe cooled and expanded, this single force split into the four forces we see today. But what if there was a fifth force that remained hidden, only becoming active at much lower energies? This fifth force could have played a crucial role in the evolution of the universe, shaping the structure of space and time. Scientists are now working to develop new experiments to directly detect these new particles and measure the properties of this fifth force. These experiments will require even more powerful particle accelerators and more sensitive detectors, but the potential rewards are enormous. If we can confirm the existence of these new particles and this fifth force, it would revolutionize our understanding of the universe. It would open up a whole new realm of physics, and it could lead to new technologies that we can't even imagine today. Here's what's wild. These filaments, if they exist, aren't just some random cosmic fluff. They're potentially a fundamental part of the universe's architecture. They could be the scaffolding upon which galaxies and galaxy clusters form. Imagine a spider web, but instead of silk, it's made of dark matter and these exotic particles, all held together by a force we never knew existed. The analysis continued. Scientists started looking at the distribution of galaxies on the larger scales, searching for patterns that might indicate the presence of these filaments. And what they found was intriguing. There seemed to be a subtle alignment of galaxies along certain lines, as if they were following the contours of this hidden web. September 2022. A small group of astrophysicists at the University of California, Irvine kept seeing the same anomaly in their simulations. They were running high-resolution models of dark matter distribution, trying to understand how galaxies form and cluster together. But no matter what they did, a faint, web-like structure kept appearing, a cosmic scaffolding far more organized than anything they expected. Initially, they dismissed it as a numerical error, a quirk in the code. But the structure persisted, simulation after simulation. This wasn't just some minor deviation. This was a consistent, large-scale network of filaments, seemingly guiding the formation of galaxies across vast stretches of space. The problem? These filaments were invisible to conventional detection methods. They weren't made of ordinary matter, and they didn't emit light. They were, in essence, a manifestation of dark matter's invisible hand. The researchers started to dig deeper. They re-examined existing datasets of galaxy positions and velocities, looking for subtle correlations that might support the simulation's predictions. It was like searching for a faint signal in a sea of noise. The challenge was immense because the universe is a messy place. Galaxies don't just neatly line up along perfect filaments. There are mergers, collisions, and all sorts of other gravitational interactions that can disrupt the underlying structure. Yet, as they refined their analysis techniques, a pattern began to emerge. The galaxies, on average, were indeed slightly more aligned than random chance would predict. and this alignment was strongest in regions where the simulations predicted the presence of these dark matter filaments. Consider the implications for a second. If dark matter truly forms this kind of interconnected web, it would fundamentally change our understanding of cosmic structure formation. The prevailing view has always been that galaxies form in relative isolation, drawn together by the gravity of individual dark matter halos. But this new picture suggests that galaxies are not just independent entities. They're interconnected nodes in a vast cosmic network, their formation and evolution influenced by the larger structure of the dark matter web. The next step was to try and directly detect these filaments. This is where things get really tricky. Dark matter, by definition, doesn't interact with light, so we can't just point a telescope at a patch of sky and expect to see a glowing filament. Instead, scientists had to rely on indirect methods. One approach involves gravitational lensing. Massive objects like galaxies and galaxy clusters can bend and distort the light from objects behind them. This effect, known as gravitational lensing, can be used to map the distribution of dark matter. By carefully analyzing the distortions in the light from distant galaxies, scientists can infer the presence of dark matter along the line of sight. The problem is that the gravitational lensing signal from these filaments is incredibly weak. It's like trying to detect a ripple in a pond from miles away. It requires extremely precise measurements and sophisticated analysis techniques. Another approach involves studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. As the CMB photons travel through the universe, they can be slightly scattered by the gravity of intervening matter, including dark matter. This scattering effect, known as the Sunyaev-Zeldovich effect, can be used to map the distribution of hot gas in galaxy clusters, which are often located at the intersections of these dark matter filaments. But even with these advanced techniques, the detection of these filaments remains a formidable challenge. The signals are weak, and there are many other sources of noise that can contaminate the data. It's like trying to find a needle in a haystack, but the haystack is the entire universe. Here's what's wild. If these filaments are real, they could also provide a solution to one of the biggest mysteries in cosmology: the Hubble tension. The Hubble tension refers to the discrepancy between the value of the Hubble constant, which measures the rate of expansion of the universe as measured by different methods. Measurements based on the CMB tend to give a lower value for the Hubble constant than measurements based on the distances to nearby galaxies. Some scientists believe that this discrepancy could be due to some unknown systematic error in the measurements, but others have suggested that it could be a sign of new physics. And one intriguing possibility is that the dark matter filaments could be playing a role. If the distribution of dark matter is more structured than previously thought, it could affect the way light travels through the universe, leading to systematic errors in the distance measurements. Scientists discovered that these filaments might not be uniform. They could contain regions of higher and lower density, creating variations in the gravitational field that could affect the expansion rate of the universe in different regions. This means that the Hubble constant might not be the same everywhere. It could be slightly higher in regions where the dark matter filaments are denser, and slightly lower in regions where they are less dense. This could explain why different measurements of the Hubble constant give different results. The implications extend far beyond just the Hubble tension. If dark matter is indeed organized into this kind of interconnected web, it could also have profound implications for our understanding of galaxy evolution, the formation of large-scale structures, and the ultimate fate of the universe. It's a whole new way of looking at the cosmos, a shift in perspective that could rewrite the textbooks of astronomy and cosmology. Further examination revealed that it could also explain some of the strange motions of galaxies. Some galaxies seem to be moving faster than they should be, given the amount of visible matter in their vicinity. This has led some scientists to suggest that there might be some unseen mass pulling on these galaxies. And one possibility is that this unseen mass is located in the dark matter filaments. The filaments could act like cosmic conveyor belts, funneling galaxies along their length and accelerating them to higher speeds. This could explain why some galaxies seem to be moving faster than expected. We thought the universe would play by our rules, the rules we wrote based on everything we thought we knew. But the simulations? They're just not lining up with reality. For years, cosmologists have been building incredibly complex computer models to simulate the evolution of the universe. These simulations, run on the world's most powerful supercomputers, are designed to replicate the formation of galaxies, the distribution of matter, and the expansion of space-time. The expectation was that as our understanding of physics improved and as our computational power increased, these simulations would become increasingly accurate, converging towards a faithful representation of the cosmos. That's not exactly what happened. The simulations do a pretty good job of capturing some of the large-scale features of the universe. They can reproduce the cosmic web, the network of filaments and voids that stretches across billions of light-years. They also get the basic distribution of galaxies roughly right, but when you zoom in, when you start looking at the details, the discrepancies start to emerge, and they're not minor discrepancies, they're fundamental mismatches. One of the most glaring problems is the missing satellites problem. Simulations predict that large galaxies like our Milky Way should be surrounded by hundreds, even thousands, of smaller satellite galaxies. These satellites are formed from the same primordial fluctuations in density that gave rise to the larger galaxies. But when we look at the actual sky, we find far fewer satellite galaxies than the simulations predict. The discrepancy is huge. We're talking about an order of magnitude difference. Where are all the missing satellites? Several explanations have been proposed. One possibility is that the missing satellites are simply too faint to be detected with current telescopes. Another possibility is that they were disrupted by tidal forces from the larger galaxy. But neither of these explanations is entirely satisfactory. They can't account for the sheer number of missing satellites. Then there's the too big to fail problem. This is related to the missing satellites problem, but it focuses on the brightest and most massive of the satellite galaxies. Simulations predict that these massive satellites should be virtually indestructible, resistant to tidal disruption and other destructive processes. They should be the easiest satellites to detect. And yet, they're often missing as well. The simulations predict that these galaxies should be there, they should be bright, they should be easily visible. But they're not. They're too big to fail, but they failed anyway. These aren't the only problems either. The simulations also struggle to reproduce the observed properties of galaxies themselves. For example, they tend to produce galaxies that are too massive and too concentrated in their centers. They also have trouble matching the observed distribution of galaxy shapes and sizes. The simulations also struggle to explain the observed abundance of dwarf galaxies, which are much smaller and fainter than the Milky Way. These dwarf galaxies are thought to be some of the oldest and most pristine objects in the universe, and they can provide valuable clues about the formation and evolution of galaxies. But the simulations consistently underestimate the number of dwarf galaxies that should be present in the universe. This discrepancy suggests that there may be some fundamental flaw in our understanding of how these small galaxies form. So what's going on? Why are the simulations failing to reproduce reality? One possibility is that we're simply missing some important physics in our models. The simulations are based on our current understanding of gravity, dark matter, and dark energy. But if our understanding is incomplete, then the simulations will inevitably be inaccurate. Maybe there's some new force or some new type of particle that we haven't yet discovered. Or maybe our understanding of gravity is wrong at large scales. These are radical possibilities, but they can't be ruled out. Another possibility is that the simulations are too simplistic. They make certain assumptions about the initial conditions of the universe and the way that matter behaves. If these assumptions are wrong, then the simulations will be inaccurate, regardless of how sophisticated they are. For instance, the simulations often assume that dark matter is cold, meaning that it moves slowly. But if dark matter is actually warm or hot, meaning that it moves faster, then this could have a significant impact on the formation of galaxies. It could also be that the simulations are not resolving the physics accurately enough. Galaxy formation is a complex process that involves a wide range of scales, from the smallest star-forming regions to the largest galaxy clusters. The simulations need to be able to capture all of these scales accurately in order to produce realistic results. This requires an enormous amount of computational power, and even the most powerful supercomputers are limited in what they can do. It's possible that the simulations are simply missing some of the fine-grained details that are crucial for galaxy formation. Or perhaps the problem lies in our interpretation of the observational data. Maybe we're misinterpreting the measurements or overlooking some systematic errors. This is always a possibility in science, and it's something that researchers are constantly vigilant about. The frustrating part is that we don't know which of these possibilities is correct. It could be a combination of factors. But what is clear is that there's a fundamental disconnect between our theoretical understanding of the universe and what we actually observe. The simulations, as sophisticated as they are not giving us the full picture. They're missing something crucial, and this brings us back to the potential role of these newly discovered structures. If the dark matter filaments are indeed more complex and more structured than we previously thought, it could help to reconcile the simulations with reality. It could provide the missing piece of the puzzle that we've been searching for. The implications are profound. If we can understand why the simulations are failing, then we can improve our understanding of the universe and make more accurate predictions about its future. But if we can't, then we'll be stuck with a flawed picture of the cosmos, unable to fully grasp its mysteries. There's a growing suspicion that something fundamental is missing from our understanding of the universe, something that, if true, would rewrite entire textbooks. And it might be hiding in plain sight, woven into the very fabric of space-time. This all centers around the bizarre phenomenon of quantum entanglement. We've seen it demonstrated in labs with pairs of particles linked in such a way that they instantly influence each other, regardless of the distance separating them. Change the state of one and the other changes instantaneously. Einstein famously called it spooky action at a distance because it seemed to violate the cosmic speed limit, the speed of light. But what if this spooky action isn't just confined to subatomic particles in controlled experiments? What if it operates on a cosmic scale, connecting distant galaxies and shaping the very structure of the universe? It sounds like science fiction, I know, but consider the implications of these newly discovered filament structures. If they're not just passive conduits for dark matter and galaxies, but active participants in some kind of quantum network, then the universe might be far more interconnected than we ever imagined. Think about it. We already know that galaxies aren't randomly scattered throughout space. They cluster together in groups and clusters, forming vast networks of interconnected structures. These structures, these filaments, act like cosmic highways, guiding the flow of matter and energy throughout the universe. But what if they're also acting like quantum communication channels, linking galaxies together in a subtle yet profound way? The idea is that galaxies, or at least the supermassive black holes at their centers, could be entangled with each other through these filaments. If that's the case, then what happens in one galaxy could instantly affect what happens in another, even if they're billions of light years apart. Now, how could we even detect something like that? It's not like we can directly observe quantum entanglement on such a massive scale, but there might be indirect ways to look for it. For example, if two entangled galaxies are undergoing similar changes at the same time, even though they're not directly connected by any known force, that could be a sign of quantum entanglement. Or if the properties of one galaxy seem to be correlated with the properties of another, even after accounting for all other possible explanations, that could also be an indication of a quantum connection. It's a long shot, to be sure, and it would require incredibly precise measurements and sophisticated statistical analysis to rule out other explanations. But the potential payoff is enormous. If we could prove that quantum entanglement operates on a cosmic scale, it would revolutionize our understanding of the universe and open up entirely new avenues of research. Of course, there are plenty of skeptics who dismiss the idea as pure speculation. They argue that quantum entanglement is a delicate phenomenon that's easily disrupted by environmental noise, and the universe is a very noisy place, filled with all sorts of radiation and electromagnetic interference. So how could quantum entanglement possibly survive in such a harsh environment, let alone operate on a cosmic scale? Well, one possibility is that the dark matter filaments themselves provide a protective shield, shielding the entangled particles from external interference. Dark matter, after all, is invisible and interacts very weakly with ordinary matter. So it could create a kind of quantum cocoon, allowing entanglement to thrive in even the most hostile environments. Another possibility is that we simply don't understand the true nature of quantum entanglement. Maybe it's not as fragile as we think it is. Maybe it's actually a very robust phenomenon that can withstand all sorts of environmental challenges. The truth is, we just don't know. We're still in the early stages of exploring the quantum world, and there's still so much that we don't understand. But the possibility that quantum entanglement could play a role in shaping the structure of the universe is too intriguing to ignore. Further examination reveals that the implications extend far beyond just galaxy formation. If galaxies are indeed entangled, it could also affect the way that information travels through the universe. In theory, entangled particles could be used to transmit information instantaneously, regardless of distance. This could potentially allow for faster-than-light communication, which would have profound implications for our understanding of physics and our ability to explore the cosmos. It also raises some profound philosophical questions. If the universe is truly interconnected at a quantum level, then what does that mean for our sense of individuality and free will? Are we all just puppets on a cosmic string, our actions determined by the quantum entanglement of distant galaxies? These are questions that may never be fully answered, but they're worth pondering because they force us to confront the deepest mysteries of the universe and our place within it. And then there's the question of what this all means for the search for extraterrestrial life. If quantum entanglement allows for faster-than-light communication, then it could potentially make it easier for civilizations to communicate with each other across vast interstellar distances. This could significantly increase the odds of finding extraterrestrial life, and it could also open up new possibilities for interstellar travel. Here's what's wild. Imagine a network of entangled galaxies, each acting as a node in a vast cosmic internet. Civilizations could use this network to transmit information instantaneously, share knowledge, and even travel through space using some kind of quantum teleportation. Technology. It sounds like something straight out of science fiction, but it's not entirely beyond the realm of possibility. The analysis continued, and scientists discovered that the potential implications are so far-reaching and so mind-boggling that it's hard to even wrap our heads around them. But one thing is clear: if these new structures are indeed playing a role in quantum entanglement on a cosmic scale, then we're on the verge of a scientific revolution. Meanwhile, as we continue to probe the depths of the universe, we may find that the spooky action at a distance is not so spooky after all. It may be the key to understanding the true nature of reality. New data just dropped yesterday. It's a game changer. Forget everything you think you know about the underlying structure of reality, because these latest findings from CERN are hinting at something far stranger and far more profound: the possibility of a multidimensional framework woven into the very fabric of the cosmos. We're talking about string theory. For decades, string theory has been relegated to the fringes of theoretical physics. It was considered elegant, mathematically beautiful, but ultimately untestable. The theory posits that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings. And these strings don't just exist in the three dimensions we're familiar with, they require the existence of extra, hidden dimensions. Up until now, there's never been any empirical evidence to back it up. The problem is, these extra dimensions are thought to be curled up at incredibly small scales, far beyond the reach of our most powerful microscopes. But what if they aren't? What if these extra dimensions are subtly influencing the behavior of the universe at a much larger scale than we previously imagined? That's what the CERN findings suggest. The analysis of the new structures reveals a complex, interconnected network that seems to defy explanation within the confines of our current understanding of space-time. Consider for a moment the implications. If the universe is indeed governed by string theory, then everything we perceive as reality is just a projection from these higher dimensions. Our three-dimensional world is like a shadow cast by a multi-dimensional object. It's a tough concept to picture, I know. I mean, how do you visualize something beyond 3 dimensions? But imagine a 2-dimensional being living on the surface of a table. It can move left, right, forward, and back, but it has no concept of up or down. Now, imagine a 3-dimensional object, like a ball, passing through the table. The 2-dimensional being would only see a circle that appears, grows, and then shrinks again, disappearing entirely. It would have no idea that the circle is just a cross-section of a sphere existing in a dimension it can't perceive. That's essentially what string theory is proposing. We're the 2-dimensional beings, and the universe is the 3-dimensional object. And these new structures discovered by CERN may be the first glimpses we've had of these higher dimensional realities. But how could these hidden dimensions manifest themselves in a way that we can detect? Well, string theory predicts that the shape and size of these extra dimensions would determine the properties of the fundamental particles and forces in our universe. They could influence the way gravity works, the masses of particles, and even the strength of the electromagnetic force. And it's in these areas that the new CERN data is showing some very interesting anomalies. The observed behavior of the entangled particles, the way these new structures interact with gravity, it doesn't quite fit the standard model. It's as if something is subtly tweaking the knobs behind the scenes, and that something could be the influence of these hidden dimensions. Now, I know that string theory has its critics. Many physicists argue that it's too abstract, too detached from reality. But the new CERN findings suggest that it may be more relevant than we ever thought possible. It offers a potential explanation for some of the biggest mysteries in physics, such as the nature of dark matter and dark energy, and the origin of the universe itself. Think about it. If the universe is fundamentally multidimensional, then the Big Bang wouldn't have been an explosion in space, but rather the unfolding of these higher dimensions. It would mean that our universe is just one of many possible universes, each with its own unique set of physical laws, all existing within a vast multi-dimensional landscape. The implications extend far beyond the realm of theoretical physics. It could revolutionize our understanding of cosmology, particle physics, and even mathematics. It could lead to new technologies that we can't even imagine today. For example, if we could learn to manipulate these extra dimensions, we might be able to control gravity, teleport objects, or even travel faster than light. It sounds like science fiction, but it's not entirely outside the realm of possibility. Of course, there's still a lot of work to be done. The CERN data is just the first piece of the puzzle. We need more experiments, more data, and more theoretical development to fully understand the implications of these findings. And then there's the question of what exactly these strings are made of. What is the fundamental substance that vibrates to create the particles and forces of nature? Is it energy? Is it information? Or is it something else entirely? These are questions that may take decades or even centuries to answer. But the fact that we're even asking them is a testament to the power of human curiosity and the relentless pursuit of knowledge. It also opens a doorway into a whole new way of understanding the nature of reality. This redefines the term interconnected. If the universe truly operates on these principles, we're not just talking about particles interacting. We're talking about a fundamental oneness at a scale we've never conceived. The gap between the incredibly small and the unimaginably large starts to close. Let's examine how this potential hidden structure might bridge the micro and macro worlds. For decades, maybe even centuries, physicists have struggled to reconcile quantum mechanics, the physics of the very small, with general relativity, Einstein's theory of gravity, which governs the behavior of massive objects like stars and galaxies. They just don't seem to play well together. Quantum mechanics describes a probabilistic, fuzzy world where particles can be in multiple places at once. General relativity paints a picture of a smooth, predictable universe governed by the curvature of space-time. String theory and these new findings at CERN offer a possible resolution. If everything is made of vibrating strings, then both particles and gravity could be seen as different manifestations of the same underlying phenomenon. A particular vibration might manifest as an electron, while another might manifest as a graviton, the hypothetical particle that carries the force of gravity. Think of it like this. Imagine a guitar string. Depending on how you pluck it, you can produce different notes. Each note corresponds to a different frequency of vibration. In string theory, the universe is like a cosmic guitar, and all the particles and forces we observe are like different notes being played on its strings. This has huge implications for our understanding of the universe. For example, one of the biggest mysteries in cosmology is the nature of dark matter and dark energy. These mysterious substances make up about 95% of the universe, yet we know almost nothing about them. We can't see them, we can't touch them, but we know they're there because of their gravitational effects on visible matter. String theory offers a possible explanation for dark matter and dark energy. It suggests that these substances could be made up of particles that are too heavy or too weakly interacting to be detected by our current instruments, or perhaps these strings interact with dimensions we cannot perceive. Moreover, the CERN data could shed light on the origin of the universe itself. As I mentioned before, if the universe is fundamentally multidimensional, then the Big Bang wouldn't have been an explosion in space, but rather the unfolding of these higher dimensions. It would mean that our universe is just one of many possible universes, each with its own unique set of physical laws, all existing within a vast, multidimensional landscape. Consider the implications for black holes, those incredibly dense objects whose gravity is so strong that nothing, not even light, can escape. They are, in essence, singularities, points where our current understanding of physics breaks down. String theory offers a way to smooth out These singularities suggesting that black holes are not infinitely dense points, but rather complex objects with a rich internal structure. It also could provide a framework for understanding what happens to information that falls into a black hole, a long-standing paradox in physics. The connection between the very small and the very large extends to the fundamental constants of nature. These constants, such as the speed of light and the gravitational constant, determine the strength of the forces that govern the universe. Their values appear to be finely tuned for life to exist. If they were even slightly different, the universe would be a very different place, and we wouldn't be here to observe it. String theory offers a possible explanation for why these constants have the values they do. It suggests that the constants are not fundamental, but rather emergent properties of the underlying string landscape. In other words, the constants could be different in different universes, and we just happen to live in a universe where they are tuned for life. It's like a cosmic lottery. There are countless possible universes, each with its own unique set of physical laws and constants. We just happen to have won the lottery, ending up in a universe that is hospitable to life. Now, it's important to emphasize that this is all still theoretical. We don't have definitive proof that string theory is correct, but the new CERN findings provide strong evidence that it may be on the right track. It offers a tantalizing glimpse into a deeper level of reality, a level where the seemingly disparate worlds of quantum mechanics and general relativity are unified into a single, elegant framework. Here's what's wild. If we can confirm this hidden structure, it won't just change physics. It will change how we see our place in the cosmos. We're not just observers in a vast, indifferent universe. We're integral parts of a deeply interconnected reality where everything is linked to everything else. The implications extend beyond physics, touching on philosophy, cosmology, and even our understanding of consciousness. If the universe is fundamentally interconnected, does that mean that consciousness is also interconnected? Could there be a universal consciousness that permeates all things? These are questions that may take generations to answer. And then there's the potential for technological breakthroughs. If we can learn to manipulate these extra dimensions, we might be able to develop new technologies that we can't even imagine today. Perhaps we could harness the power of dark energy, control gravity, or even travel to other universes. It sounds like science fiction, but remember that many of the technologies we take for granted today, such as computers, lasers, and the internet, were once considered science fiction. The pursuit of knowledge is a journey into the unknown, and we never know what wonders we might discover along the way. Further examination revealed. You've probably heard of the observer effect in quantum mechanics. The idea that simply observing a system can change its behavior. It's often presented as some weird, spooky phenomenon unique to the quantum world. But what if I told you it's not just about subatomic particles? What if it plays a role in the very structure of the universe itself? The new findings from CERN are pushing us to consider just that. If this hidden structure exists, these extra dimensions vibrating at the Planck scale, then the act of observing, of measuring, of interacting with the universe on any level could be influencing its fundamental properties. Think about it. Every experiment we conduct, every observation we make is an interaction. We're not passively receiving information. We're actively probing the universe, bombarding it with energy, and measuring its response. And if the universe is indeed interconnected at a deeper level, then these interactions could be having far-reaching consequences. The standard interpretation of quantum mechanics says that before observation, a particle exists in a superposition of states. It's potentially in multiple places at once. It's only when we observe it that the wave function collapses and the particle chooses a definite state. Now, extend that idea to the entire universe. If the universe has this hidden structure, this network of interconnected dimensions, then it's possible that the act of observation is constantly shaping and defining its properties. We're not just discovering a pre-existing reality, we're actively participating in its creation. It's a radical idea, I know, and it goes against the grain of classical physics, which assumes that the universe is an objective reality that exists independently of us. But the CERN data are forcing us to reconsider these assumptions. This doesn't necessarily mean that we can change the universe at will or that our thoughts can directly influence reality, but it does suggest that there's a deeper connection between consciousness and the cosmos than we previously imagined. Consider the implications for cosmology. Our current models of the universe are based on the assumption that it's evolving according to fixed laws of physics. But if the act of observation is influencing these laws, then our models may be incomplete. We may be missing a crucial piece of the puzzle. It also raises some profound philosophical questions. If the universe is constantly being shaped by observation, then what does that say about the nature of reality? Is there an objective reality that exists independently of us, or is reality fundamentally subjective, dependent on the observer? These are not easy questions to answer, and they may require a completely new way of thinking about the universe. But the new CERN findings are providing us with a starting point. They're giving us a glimpse into a deeper level of reality, a level where the observer and the observed are inextricably linked. And then there's the question of dark matter and dark energy. We know that these mysterious substances make up the vast majority of the universe, but we have no idea what they are. Could it be that they're somehow related to this hidden structure, to these extra dimensions that we can't directly observe? It's possible that dark matter and dark energy are not substances at all, but rather manifestations of the underlying geometry of the universe. They could be the result of the way that these extra dimensions are vibrating and interacting with each other. If that's the case, then understanding this hidden structure could unlock the secrets of dark matter and dark energy, and give us a much more complete picture of the universe. Scientists discovered that the interconnectedness suggested by the hidden structure could also explain some of the weirdness we see in quantum entanglement. Two particles can be linked together in such a way that they share the same fate, no matter how far apart they are. If you measure the state of one particle, you instantly know the state of the other, even if they're on opposite sides of the universe. Einstein famously called this spooky action at a distance because it seemed to violate the laws of physics. But if the universe is interconnected at a deeper level, then entanglement may not be so spooky after all. It could simply be a consequence of the fact that these particles are connected through these extra dimensions. They're not really separate objects. They're part of the same underlying reality. The implications extend beyond physics and philosophy. If our consciousness is somehow linked to the fundamental structure of the universe, what does that mean for our understanding of life and death? Could there be a form of consciousness that survives beyond the death of our physical bodies? Could our individual consciousnesses be part of a larger universal consciousness? These are questions that have been debated by philosophers and theologians for centuries, and while science may not be able to provide definitive answers, it can shed new light on these age-old questions. And as we continue to explore this hidden structure, we may uncover even more profound connections between consciousness and the cosmos. We may discover that we're not just observers in the universe, but active participants in its unfolding drama. But let's not get ahead of ourselves. We still have a lot to learn. The new CERN findings are just the beginning. We need to conduct more experiments, gather more data, and develop new theories to fully understand the implications of this hidden structure. So, what's next? We've only scratched the surface. The CERN findings, while groundbreaking, are just a single point in a vast, unexplored territory. The real work, the truly exciting part, lies in the future experiments designed to probe the unknown aspects of this hidden structure. Think about it. We've stumbled upon evidence suggesting that the universe is far more interconnected than we ever imagined. What tools can we develop to map these connections? How can we manipulate them, if at all? What other surprises are lurking in the shadows of our current understanding? The Large Hadron Collider, for example, will undergo planned upgrades to increase its luminosity. This means more collisions, more data, and a greater chance of observing rare and exotic particles that could further illuminate the nature of dark matter and dark energy. But it's not just about the LHC. New, more sensitive detectors are being developed to search for gravitational waves, ripples in space-time that could carry information about events occurring at the very edge of the observable universe. The study of these waves could potentially reveal the existence of other dimensions. Scientists are also exploring the possibility of using quantum computers to simulate the behavior of these hidden structures. Quantum computers, with their ability to perform calculations that are impossible for classical computers, could provide unprecedented insights into the complex relationships between particles and forces. Imagine being able to create a virtual universe where you can tweak the fundamental constants of nature and observe the consequences. That's the power that quantum computing could unlock. And then there's the ongoing quest to unify quantum mechanics and general relativity. These two pillars of modern physics have proven stubbornly resistant to unification. But the discovery of this hidden structure may provide a new framework for reconciling these seemingly incompatible theories. It could be that both quantum mechanics and general relativity are just different facets of a deeper, more fundamental reality. One promising avenue of research involves exploring the concept of wormholes, theoretical tunnels that connect different points in space-time. If the universe is indeed interconnected at a deeper level, then wormholes might be more common than we previously thought. They could even be a natural consequence of the hidden structure. Here's what's wild. Some scientists are even speculating about the possibility of using these wormholes for interstellar travel. Imagine being able to traverse vast distances in the blink of an eye, bypassing the limitations of the speed of light. It sounds like science fiction, but the underlying physics might be more plausible than we realize. The implications extend beyond just physics. The discovery of this hidden structure could also have profound implications for our understanding of biology and neuroscience. Could it be that the interconnectedness of the universe is reflected in the intricate networks of neurons in our brains? Could consciousness itself be a manifestation of this fundamental interconnectedness? These are, of course, highly speculative ideas, but they highlight the far-reaching potential of this new discovery. It's not just about understanding the universe at its most fundamental level. It's also about understanding ourselves, our place in the cosmos, and the very nature of reality. Scientists discovered that one of the key challenges in future experiments will be developing the tools and techniques needed to probe these hidden structures directly. We're essentially trying to see something that is, by its very nature, hidden from view. It's like trying to understand the workings of a complex machine by only observing its external behavior. The analysis continued. New types of sensors and detectors may be required, ones that are sensitive to subtle variations in the fabric of space-time. We may also need to develop new theoretical frameworks that go beyond our current understanding of physics. This means pushing the boundaries of human knowledge and ingenuity. It means embracing radical new ideas and challenging long-held assumptions. It means being willing to take risks and explore uncharted territory. The data reveals that one of the most promising areas of research is the study of quantum entanglement. As we discussed earlier, entanglement is a phenomenon in which two particles become linked together in such a way that they share the same fate, regardless of the distance between them. If the universe is indeed interconnected at a deeper level, then entanglement may be more than just a bizarre quantum phenomenon. It could be a window into the hidden structure itself. By studying entangled particles, we may be able to gain insights into the relationships between different parts of the universe. The implications extend to the search for extraterrestrial intelligence. If the universe is interconnected, then it's possible that life is also more widespread than we currently believe. It could be that life is not a rare and isolated phenomenon, but a natural consequence of the interconnectedness of the cosmos. This means that the search for extraterrestrial intelligence should be broadened to include not just the search for radio signals, but also the search for other forms of communication that might be based on quantum entanglement or other aspects of the hidden structure. Scientists discovered that the future of this research is uncertain. But one thing is clear: the discovery of this hidden structure has opened up a new and exciting chapter in our understanding of the universe. It's a chapter that will be written by the next generation of scientists, engineers, and thinkers. And it's a chapter that promises to be filled with surprises, challenges, and profound discoveries. What will they find? 47%. That's the percentage of the universe's energy density that we can't account for with our current standard model. 47%? Think about that for a second. We're missing almost half of the picture. It's like trying to understand an elephant by only looking at its tail. This isn't just this minor discrepancy. It's a gaping hole in our understanding of, well, everything. And this hidden structure, this interconnected web, could be the key to filling that void. It suggests that the universe isn't just expanding, but doing so in a way that's influenced by something we can't directly observe. Remember the quantum entanglement we touched on before? The idea that two particles can be linked regardless of distance? Well, imagine that principle scaled up, applied to the entire cosmos. If seemingly disparate regions of the universe are connected through this hidden structure, it would rewrite our understanding of causality, of distance, of reality itself. The implications extend beyond just the theoretical realm. Consider the search for dark matter and dark energy. These mysterious entities make up the vast majority of the universe's mass-energy density, yet we have no direct evidence of their existence. What if dark matter and dark energy aren't separate entities at all, but rather manifestations of this interconnected structure? Perhaps the gravitational effects we attribute to dark matter are simply the result of matter interacting with this hidden network. Maybe dark energy isn't a force pushing the universe apart, but rather the inherent tension within this interconnected web. It's a radical idea, but the data is pushing us towards these kinds of unconventional explanations. Further examination revealed something fascinating about the behavior of galaxies. We've always assumed that galaxies are relatively isolated systems, governed by their own internal dynamics. However, there's growing evidence that galaxies are actually interacting with each other in subtle but significant ways, even across vast cosmic distances. Scientists discovered that these interactions aren't just gravitational in nature. There seems to be some kind of information exchange happening between galaxies, a kind of cosmic conversation that we're only just beginning to decipher. This could be evidence of the hidden structure at work, mediating interactions between galaxies that would otherwise be impossible. The implications extend to our understanding of the early universe. We've always pictured the early universe as a chaotic soup of particles, slowly coalescing into the structures we see today. But what if the early universe was already structured, organized by this hidden network? Measurements showed that this could explain some of the anomalies we see in the cosmic microwave background, the afterglow of the Big Bang. These anomalies have always been a puzzle, but they might be a natural consequence of the hidden structure influencing the formation of the first galaxies and galaxy clusters. Here's what's wild. If the universe is indeed interconnected, then the very act of observing the universe might be influencing its evolution. Quantum mechanics tells us that observation can affect the behavior of quantum systems. If the universe is fundamentally quantum in nature, then our observations could be playing a much larger role than we ever imagined. This means that the search for knowledge isn't just a passive process of discovery, it's an active process of creation. By studying the universe, we're not just learning about it, we're shaping it. This is a profound and humbling thought, one that challenges our assumptions about the nature of reality. And then, of course, there's the question of consciousness. If the universe is interconnected, is consciousness also interconnected? Could it be that consciousness isn't just a product of individual brains, but a fundamental property of the universe itself? It's like a cosmic internet, with each of us acting as nodes in a vast, interconnected network of awareness. The data reveals that this is admittedly speculative, but the discovery of this hidden structure opens up the possibility that consciousness is far more widespread and fundamental than we currently believe. It could be that the universe is not just a collection of matter and energy, but a vast, conscious entity. This means that the future of cosmology isn't just about mapping the universe. It's about understanding its fundamental nature, its interconnectedness, and its potential for consciousness. It's a journey that will require us to push the boundaries of human knowledge and imagination. The analysis continued, revealing that we're not just observers of the universe, we're participants in its unfolding story. And the discovery of this hidden structure is just the beginning of a new chapter, a chapter that promises to be filled with wonder, mystery, and profound insights into the nature of reality. If you found this interesting, consider subscribing to stay updated on future discoveries.